Okay, we're going to start our Unit 2, and the first main lesson is on logic problems. So we'll go through a few examples here, and there'll be lots of examples we'll do in class and look at different logic puzzles and things like that. So first of all, this one you can see we got a series of triangles. So the idea is if we keep adding another row to the pyramid, how many triangles will we end up getting? So you can see here this Georgia, she makes a conjecture. A conjecture is just an educated guess that you can actually test to see if it's true or not. So her conjecture is that by the time she continues the pattern and gets to 10, the level 10 of the pyramids, that there should be 100 triangles total. So would it make sense for us to draw all 10 of them and then count them up? No, it's better off just to look for a pattern to see if we can figure out if it's true. So let's just kind of use a little table for this one. So you can see that if we have one triangle, right? Figure 1 gives us one triangle, and that's it. So now we go to figure 2. You look at the second one, you can see we got 1, 2, 3, 4 triangles. Go to level 3, we got 1, 2, 3, 4, 5, 6, 7, 8, 9 triangles, and that should be enough to figure out our pattern. So look at these numbers. Can you see a pattern? So the idea is she's saying that by the time you get to 10, there should be 100 different triangles. Okay? So the guess is, or our conjecture that we're saying is that true? How do we prove it? So let's just do one more row just to see if it would be true or not. So let's just manually draw on a couple of triangles here for one more row. So something like that. So you can see I added 1, 2, 3, 4, 5, 6, 7 more. So we actually then are level 4. We added 7 more triangles, so that would be 16. So if we added another row, we could try one more. So if we did one more row, we'd end up with, oops, I ran out of room. I keep flipping pages here, so you'll see that we'd end up with 1, 2, 3, 4, 5, 6, 7, 8, 9 more. So if we add 9 more on, we would get 25. So you can see we're just keeping adding a new row. Our numbers will keep getting bigger and bigger. So I think we've got the pattern figured out. Let's see if we can make sense of it. So if you look at the first one, we got 1 to 1, then 2 to 4, 3 to 9, 4 to 16. The pattern to this one is you can see each of these numbers is just the first number times itself. So 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25. So if we get down to 10, we'd get 10 squared. Is 10 squared equal to 100? Yes. So her conjecture is right. So that's just an example to kind of show you the logic that you have to do to solve some of these. Okay, there's a few questions in the book here. Let's just take a quick look at them. So this one's saying if we take a quadrilateral, a polygon, and we divide it into the fewest number of triangles, we get a pattern. So you can see this first one, we have a four-sided shape. We divide it into 2 triangles just by cutting it in half. Then you can see the next one, for the pentagon, we got a 5-sided shape. So we'd make 2 lines, we'd end up getting 3 triangles. The hexagon, we got a 6-sided shape, and we end up getting 4 triangles. So you can see the pattern is here. It seems to be that as we increase more and more sides, we're getting 2 less triangles. So if our question was how many triangles would a 10-sided shape be, our conjecture then would be 8. We'd have 2 less sides, or 2 less triangles than the number of sides. So that's just a fairly easy example. Let's skip 7. Let's look at number 8. It says we see a pattern in the multiples of 3. So if we do a list of all the multiples of 3, his conjecture is they'll always add up to 3, 6, or 9. So you can see it goes 3, 6, 9, 3, 6, 9, and so on. So any multiple of 3 tends to be, the sum of those digits always ends up being 3, 6, or 9. So 3, 6, 9 obviously work. Then we go 12, 15, 18, all the way up to 30 in this table, and it seems to work. So if we kept going, let's just try a couple more. So if you had 33, the 2 digits added up would give you 6, so that one works. If we do 36, that would give us 9, so that one seems to work. The next one would be 39. So what happens when we have 39? We add up those two digits, we get 12. So are we still following the pattern of 3, 6, 9? No. So 39 is what we call a counter example. It's now showing that this pattern doesn't always work. Or we could just change our conjecture. So if the conjecture is that any digit that is a multiple of 3 will always add up to 3, 6, or 9, we just found an example that doesn't work. 39 doesn't work. And if we tried the next one we did, 42, it's back to 6. It would work. But if we got to 49, it's going to be at 15. So you're going to see that things will, 48 I guess, it'd be at 12 just like this one. Okay, so the idea is you're going to get to cases that don't work, so we just say, well, we found a counterexample, so that conjecture is not true. Or, in a case like this, we just change our conjecture. So we say, all numbers add up to 3, 6, 9, and if you get a number that's not, add them again, like a 2-digit number. So if we get a 2-digit answer, like in this case 12, add those two together, we're back to a 3. Okay, so that could be a modification or conjecture saying all multiples of 3 will add up to 3, 6, or 9. And if it's a 2-digit number or 3-digit number, just keep adding those digits down till you get to 1 digit, and it should always be 3, 6, or 9. And we could test it a bit more. Let's suppose we wanted to try a large number like 66 is a multiple of 3. Add those together, we would get 12. Add those together again, we get 3. So it seems to work. And we could try a really big number. Let's do one more. Let's try a big number like let's do in the thousands. So if we had a number like 3, 3, 3, 3, add all those up, we get 3, 6, 9, 12. Add those up again, we get 3. So that seemed to work. And even if we changed, we could make this something different. Let's suppose it was 3, 3, 6, 6. So now you can see we'd have 3 plus 3 plus 6 plus 6 is now 18. So if we add those up again, 1 plus 8 is 9. So it seems to work. So our conjecture, I think, if we say just keep adding up all the digits down until you get to 1 digit, it should always be 3, 6, or 9. Okay, this circle one we're actually going to do in class. There's an applet listed below, and we'll test that one out there, but we'll just kind of get started here. So you can see the conjecture is if we divide a circle up, so if we use 2 points on a circle, we get 2 regions, right? We have 2 dots here, we got 2 different regions. If we use three points, we connect all the points, you can see we end up getting 4 regions. If we do 4 dots, we get all those regions, we end up with 8 regions. So her conjecture is if we increase the number of dots, we just keep doubling the number of regions. So her theory is if we go into 5, we'd have 16 regions. If we go to 6, we'd have 32, and so on. So what we're going to do is I'm going to leave you with that one. You can think about it to see if it's actually true or not. And if you want to draw these out, you could try it. But there's a little applet down below the lesson, and we'll take a look at that in class, or you can try it on your own to see if it's going to work. Here's another one. It says if we follow this number pattern that we should follow the results. We went add those, multiply and add those numbers, we get 9. Add them again, we get 98, so on. So you can see the numbers are going 9, 8, 7, 6. So the question is, if we keep doing this, will it actually be true? So it's asking, what would a counterexample be to show that that's wrong? So we could keep going. So if we went 1, 2, 3, 4, we could go up to 1, 2, 3, 4, 5. But let's skip a few. Let's go 1, 2, 3, 4, 5, 6, 7. And let's times it by 8. And then we'd add on a 7. If you do that on your calculator, we end up with an answer. Let me grab my calculator, make sure it works. So we have 1, 2, 3, 4, 5, 6, 7 times 8 plus 7. Our answer is 9, 8, 7, 6, 5, 4, 3. So it seems like it's following the pattern, so that's good. So if we keep going, we go to 8, it should be, right, if we add on an 8, we should get a 2 on the end. If we add on a 9, we should get down to 1. But what happens now if we go beyond 1 to 9? So let's try 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I don't know if that works with a 10. Times 8 plus 10. So let's try that. So let me try that on my calculator. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times 8 plus 10, and now it doesn't follow the pattern. So what we did is we see once we got to 10, it's no longer, it's sort of a 2-digit number, so this conjecture seems to be that it only works from 1 to 9. So this one doesn't work. That would be considered our counter example for that question. Okay, here's a few practice ones. Same thing, we won't do all these, but the first one, it's saying, can you rearrange the golf ball so that the triangle's upside down? So what you want to do is move the balls downwards so you'd have an upside down triangle instead of right side up. And there's an applet down below where you can actually try this to see if you can get the right number of moves. The minimum number of moves you can move it in is 3, so I want you to try that game to see if you can figure out how to do it in 3 moves to get the triangle totally upside down. Number 5 on here says sort of like a magic triangle, magic square kind of thing. So it's saying put the numbers 1 to 9 all around the circle so that they add up to 17. So we need each side to add up to 17, so maybe you could go 1 on the top, and we need to add up to 17, so let's go 1 plus 9, that would add up to 10, and then we need a 3 and a 4 to add up to 7, and then we could keep going, so maybe we do a 2 over here, so 9 plus 2 would be 11. We need 5 more, so let's do or 6 more we would need, so you could do a 5 and a 1, but we already used the 1. So the idea is, could we put numbers all the way around here? So we'd have 8, 7, 5, and 6, and so on. So we want to rearrange those numbers so that we get 17 on all 3 sides. So obviously this isn't going to work, I got way too many, but I want you to play with it to see if you could get that one to work. Okay, the number 6 here is a magic square, which just basically says every row and column will add up to the same thing. So in this example, all the numbers add up to 36. Okay, so you can just test to see how that works. So we're going to look at questions where you'll get some of these and you have to rearrange them to see if you can get them to add up to the same. So whether it's a triangle, square, same sort of thing. And that's it. So we'll stop there. We've got lots of practice questions that we'll be working on in different types of puzzles. So next time, see ya.